Particle with a mass of 4 kilograms is acted upon by 4 forces with magnitudes as shown here and directions as shown over here. And we want to know what's the acceleration of the particle. To start, we're going to draw a free body diagram. Luckily, this is effectively a free body diagram already. We now want to be able to resolve this onto our coordinate axes. So F3 is in the negative direction, F4 is in the positive direction, F2 is in the negative y direction. F1 is going a little bit to the right and a little bit up. So we'll point out that we can resolve that into x and y components here to be able to write them in our x and y equations. Where are those equations coming from? Newton's second law. So here we have Newton's second law, the sums of the forces are equal to mass times acceleration. As a vector expression, that just looks like F1 plus F2 plus F3 plus F4, that's my net force, is equal to mass times acceleration. But in order to solve for my acceleration, it's going to be easier if I split this up into x components and y components. So we'll go ahead and do that. So considering the x components first, that sums of my forces are going to equal the x components of each of those forces. And looking at this, F2 and F4 are only up and down, so they have no x components. F1, the x component, is going to be the magnitude of F1 times the cosine of 30 degrees to project that onto the x-axis. F3 is just going to be negative F3, whatever that value is, 5. So in writing this, we should have 10 times cosine of 30 degrees plus 0 minus 5 plus 0. Here we go. And that equals mass times acceleration in the x. Where here I've left off the units to make it look a little bit cleaner, and I've just said all forces are units of newtons here to keep track. We can now divide both sides by the mass, and we can solve for the x component of my acceleration as 0.92 meters per second squared. We have the x component. Next step is to find the y component, and then we can recombine them to get the total acceleration. The y component will look very similar. We take the y components of each of these forces, and now we'll note that F3 should be 0. F1 will now be F1 sine of 30 degrees to get the y component. And then F2 and F4 are positive and negative. F4 is positive, F2 is negative. So plugging those in, we get 10 sine 30 degrees to get the y component, minus 40 for my force 2, 0 for my force 3 because it's not going up or down at all, and then positive 2 for my force 4 because force 4 is 2 newtons and it's going straight up. We can then solve this by dividing by mass on both sides, plugging in our numbers, and we get an acceleration of negative 8.3 meters per second squared. And you might have anticipated this given how strong F2 is compared to the other forces that are pulling up. If these are drawn proportionally, that's what we'd expect. The only remaining step is to combine these. We have component-wise what our acceleration is, and we can combine them and say that my total acceleration is then the x component in the I hat direction plus the y component in the j hat direction. Or this, 0.92 I hat minus 8.3 j hat with units of meters per second squared. If you want that as a magnitude and direction, you can do what we've done in the past, which is square the x and the y components, add them, take the square root to get the magnitude, and then take the inverse tangent of the y over the x to get the angle. And here that would give you 8.4 as our overall magnitude with the direction of 84 degrees below the horizontal. Or if you prefer, I guess you could write that as 8.4 meters per second squared with an angle of 276 degrees above the horizontal as it wraps all the way around. So it's kind of going diagonally down here is the net acceleration that this particle will feel.